So hi and welcome to part 2 of my I/O Expander mini-series. In part 1 we were specifying out the project and specifying some of the components that we intend to use. We drew up a first draft at a schematic diagram, and then we started to search for and order some of the components. So what we'll be doing this time is taking a look at those components, getting them built up onto a breadboard. Then we can start taking some measurements and calculating how much current we're going to be using, just making sure that we're happy with the circuit. And then finally we'll be connecting it to an Arduino just to prove the concept does actually work. So I've got all the components now, everything has arrived. These are the capacitors. I think these were 330 nanofarads and these were 10 nanofarads. I think they came from the same supplier. Don't actually remember who the supplier was now, but I know they came from eBay, so that's those. Then we got the actual IC itself. Now this is how it came in a little tube. I've taken it out because I've actually been playing around with it, but that was the IC. And then we had the voltage regulators, the 78L05s from Bright Components. Now I was actually impressed with Bright Components because they're the only supplier that actually supplied their components inside one of these foil bags. Now these are, I don't know if anti-static is the correct terminology, but these are the correct bags to protect against static damaging the components. The static voltage you can sort of pick up on your hands if you've been walking around on a carpet or something, and you may have a charge on you, and when you touch the bag, that voltage will go into the bag and damage the components. So this is the correct type of bag, this foil bag. Whereas if you look at these types of bags, these are clearly not. I think sometimes they come in a pink bubble wrap, which again I don't think is the correct thing to protect against static. That pink bubble wrap I believe is called anti-static bubble wrap, but it's not the right thing to protect the components. They should be in these foil bags. These aren't a problem because they're just capacitors. It's not really a big issue, but I do see a lot of components, particularly the way this chip has came. It's not really correctly packaged, but this is the sort of thing you're going to get when you buy dirt cheap components from eBay. You're getting a bargain, and some of the cost cutting there is not using the correct packaging. Hopefully we won't have a problem with the chip being damaged, but it is just something you have to be aware of. If you are buying cheap components, you can't really rely on the supplier using the correct packaging. The other thing I wanted to say about Bright Components is they were kind enough to send me a voucher, which I thought was a really nice touch. 10% discount voucher, use as many times as you like on orders made on our online store, and they've got their website there, and they give you a voucher code. I've covered it up because I didn't think that it was fair for me to just be sharing out the code to just anyone. I didn't think that was really fair on them, so I've covered it up. And it actually says it's valid until the 31st of December 2021. I've only just noticed that. I assumed it was the 31st of December 2020, but it's actually 2021. So this voucher lasts for a whole year. 10%, use as many times as you like. So that's really great. So I'm going to be checking them out again and buying components from them in the future. We'll just say they're not sponsoring the video. I was just impressed with their packaging and impressed with the voucher that they included. And for the other components we need, I'm just going to use the components that I've already got in my stock. So let's move on to get some of these parts put onto the breadboard to start building up the circuit. So the first thing I've put onto the breadboard is the little voltage regulator. It's a little tricky to see down in here. It's just there. And I've basically got the input and output capacitors. Now the center pin on the voltage regulator is the ground, so I've got the input capacitor connected to the center pin and to the pin on the right, and then I've got the small output capacitor there connected across the center pin and the pin on the left. and I've got the flat edge of the voltage regulator towards the bottom of the screen as we're looking at it here. Then I've connected some input lines, so I've got a positive and a negative on the input line and a positive and negative on the output line. And then just here I've got a 9-volt power supply coming in, so we should have 9 volts across the top rail, and then that regulated down to 5 volts on the bottom rail. So if we put the voltmeter across the input, which is the top rail, so you can see there we've got just over 9 volts on the input. And then if we move the meter across to the output on the bottom rail, you can see there we've got actually a little bit under 5 volts, 4.82. Now next I wanted to decide on the current limiting resistor for the LEDs, and I thought a good starting point was 330 ohms. But what I want to do is I want to measure the current that's going through these. So I'm going to measure the resistance of the... So I'm going to measure the resistance of this LED just to check how close it is to 330. That's over range because we're on 200 ohms, so we need to go up to 2000 ohms. We could see it's pretty close to 330. It's actually 327 if we want to be accurate. And what I'm going to do is I'm going to measure the voltage across this to calculate the current that's flowing through the LED. So I've just got the resistor across the 5 volts going to the LED, and then the LED down to ground. And you can see the red LED is quite bright there. It's a bit difficult to see on camera how bright that is, but that is it's probably about the kind of level that you would want it at. It's not over bright, but it's not too dim either. Now if we measure the voltage across this resistor, we should be able to calculate with a bit of Ohm's law how much current is flowing through there. So we'll put this meter back on voltage. So we've got about 2.93 volts across that. So that works out to be about 9.9 milliamps. Quite a bit lower than I thought actually. So then what I've done next, I've added a 200 ohm variable resistor in here. It's actually measuring a little bit more than 200 ohms. So I've got it turned fully one way. And I've measured the voltage across the 330 ohm resistor again. And I think I'm now getting about 1.6 volts. About 1.66 volts, and that works out to be about 6 milliamps. So I'm trying to get the current as low as I can without making the LED too dim, and to be honest, that is still fairly bright. I think we could even go a higher resistance than that. If I turn the potentiometer, I don't think you'll even be able to see the difference. It's just slightly brighter. There's hardly any difference at all, so I'm happy with the higher resistance, and we'll get lower current. I'm trying to keep the current as low as possible because I'm thinking about the maximum 100 milliamp limit that we have on our power supply. So if we got each LED taking like 10 milliamps each. That's 20 milliamps off of our power supply before we even start. So I want to keep these as low as possible. So then what I did is I actually removed the power off the circuit and disconnected the wire going to the LED, and then I measured the resistance of the combined variable resistor and our fixed resistor here, and the total resistance came to 590 ohms. So that's kind of roughly where I want to be, 590 ohms. I think the closest resistor I've got to that will be 560 ohms, so that's what I'll go with. So then next I brought in the BC547 transistor, and I've connected the LED circuit up to its collector and connected its emitter down to ground, and then the center pin is the base. I've connected that up to this 1k resistor, and I've measured that, and it is pretty close to 1k. And then I've got a variable resistor in series with it, and again the other side going out to the plus 5 volts. So if we measure our voltage across this known resistor value, we should again be able to calculate the base current. And what I did, I played around with different values of the variable resistor, starting low and then gradually sort of building higher and higher. And I've got up to a 20k resistor fully wound up. It's given us 21k of resistance across here, and then I've measured the voltage on here, and we're getting, let's see, 0.19 volts, and I calculated that to be 0.19 of a milliamp, so about 0.2 milliamps. Now I did find that I could keep going higher and higher with this, but I didn't want to go ridiculously high, sort of in fear of something being sort of slightly unstable in the circuit. If the currents were too low, I'd be a little bit concerned we're not fully turning on the transistor. What I also did is I just checked again the current through the resistor circuit, the current limiting resistor circuit, by again measuring the voltage on that. 1.59 volts, which works out at 4.82 milliamps. I think that's slightly lower than we had without the transistor in there. I think there's a little bit of a voltage drop across the transistor, but it's still kind of in the ballpark of where I want to be. So I think I'm pretty happy with that. I think they're the values I'm going to go with. I'm going to go with a 560 ohm resistor as a current limiting resistor for the LED, and I'm going to go with 22 kilo ohms for the base resistor on the transistor. I think I'm pretty happy with those values. Next I've popped in my MCP 23008 chip, and I've connected up my 3 address lines and the reset line. So I've got pins 3 and 4, these two here, they're tied to low, and they are the A2 and A1 address pins. The next pin is pin 5, which I've got a 10k resistor pulling that up to the 5 volt line. That's the address pin A0, and then the next one along is pin 6, which is the reset pin, and again I've got that pulled up with a 10k resistor to the 5 volt line. So next I'll connect one of the GPIO pins to be the input of our base of our transistor. So GP0 is pin 10. So if this is pin 6, that's 7, 8, 9. So this must be pin 10 here, the first one on the other side. So I'll go in there and we'll take that into our base of our transistor. through these resistors here into the base of the transistor. So I guess what we need next is power. So the positive is pin 18, that must be the last pin on this side. We'll take that to the 5-volt rail. And then pin 9 is the ground, which is the last pin on this side. Take that down to ground. Now I haven't got my 100 nanofarad capacitor in this circuit. I think I'll get away with not having it. I'm not really sure if it's required anyway, but I will include it in the final design. Just don't have one to hand right now. So I think the only other things we need to connect are the I2C bus, and for that I'm going to need an Arduino. So I'll just quickly go over the connections between our circuit and the Arduino. So firstly we've got the SCL line on our chip on pin 1, and if we follow this across to the Arduino we can see we've got that going into A5 on the Arduino. That's the Arduino's clock line. And then we've got our data line for our I2C on pin 2, and I've got that going across into pin A4 on the Arduino. And then the only other connection I've made is the ground, just make sure that both of our systems are referenced to the same ground, 0 voltage. So we've got ground on the Arduino here, going to the ground rail on our board. That's important, just to make sure that all the grounds are at the same level. So now I'm in the Arduino IDE, and I thought I'd just show you something that I'd found, because I thought this was quite useful. If we go down here and look for the wire folder, and then we can see something in here called an I2C scanner. So if we just click on that, now this is a handy little utility script that can scan for devices on the bus, on the I2C bus. So I thought this would be quite useful, because I haven't really given any thought to what the address is of my circuit. I know that we can toggle the lower bit, but I haven't looked at all the other bits, so I don't know what the actual address is of our device. So I thought we could use this to scan for it. So if we just upload this, now I have speeded this up a little bit because it did take a little while to compile. You can see it's now uploading. So now if we take a look in the serial monitor, we can see it's scanning, and we can see it's already found our device. I2C device found at address 0x21. So that's hex 21. So that's the address of our device. So I thought that was quite useful, quite handy. So next I've written a little script of my own just to demonstrate how our circuit works, how we can communicate with our circuit and control the I/O pins. So you can see we include the wire library, and then we have our setup script. The first thing we do here is call wire.begin, and then we do a wire.begin transmission, and we use our address there that we just discovered. Next we do wire.write, and we send a 0 to that. Now that's to select which register we want to write to, and register 0 is the IO-dir register. Then next we call wire.write again and send another byte, and again we're sending 0. Now this is actually the value that's going into the register, and by setting all the bits to 0 we're setting all the GP pins to be outputs. And then finally we call wire.end transmission. So that's basically how we write data into our chip. And then here we have the main loop. So this is quite simple. I'm just calling delay 500, that's a half a second delay. And I'm calling this output function. We'll have a look at that in a second, but it takes three parameters. The first parameter is the address of the device. The second parameter is the address of the register that we want to write to. And then the third parameter is the value that we're writing to. And you can see there I'm sending it a binary 1 just to switch on the lower bit. So that will turn on GP pin 0, which is the first pin. And then I'm just doing a delay 250, that's 250 milliseconds, so it's a quarter second delay. And again, calling the output function again, three parameters again, but this time the last parameter is binary 0. And that's just to turn the pin off. So then we've got this output function that I've written here. And you can see it takes 3 bytes as the 3 arguments. The first argument is the address. Second argument is the register. And the third argument is the value that we're going to put into the register. And it's pretty much the same as before. We just call wire.begin transmission with the address, and then wire.write with the register, and then wire.write with the value, and then finally wire.end transmission. So if we run this, we should just see it turns the pin on and off. So I'll upload that. Now this time this is in real time, it didn't take too long to compile this. You can see it's uploading and it's done. And then if we look over here, we can actually see the circuit is working. The LED is flashing here exactly as we expected. So that's great. We've got the circuit built up on the breadboard. We've looked at the currents that are going through the different parts of the circuit. We're happy with everything, and we've proved that the concept works by programming an Arduino and connecting it up, and we've actually got the communication going across our I2C bus, and everything's working as expected. So that's great. So what we'll do in the next video, we'll start to think about designing a printed circuit board so that we can tidy all of this up and get it all looking really neat on our own little specifically designed PCB. So I hope to see you next time in part 3.